Welcome to Little English Studio, the channel where science, exploration, and human curiosity come alive in clear and captivating English. Today we embark on a journey to the hidden depths of our planet, far below the waves that glimmer on the surface, to a world that is largely unseen yet shapes our climate, supports diverse ecosystems, and holds secrets of Earth's history. This is the story of mapping the global seafloor, a monumental scientific endeavor that combines satellites, sonar, submersibles, and international collaboration to reveal the topography of the ocean floor, from deep trenches and sprawling abyssal plains to undersea mountains and volcanic ridges. Join me as we explore how scientists transform the opaque, dark expanses of the oceans into detailed, three-dimensional maps, why these maps are crucial for understanding climate, geology, and marine life, and how humanity is piecing together a global view of the Earth beneath the waves. A pursuit that combines cutting-edge technology with the curiosity and perseverance that have always driven exploration. The oceans cover over 70% of the Earth's surface, yet more than 80% of the seafloor remains unmapped in high resolution. For centuries, the depth and contours of the ocean were known only through guesswork, sailor reports, and primitive sounding methods. Early explorers dropped weighted lines from ships to measure depth, but this method was slow, imprecise, and limited to shipping lanes and accessible regions. It was only in the 20th century, with the advent of sonar and echo-sounding technology, that scientists began to obtain a more continuous picture of underwater topography. Sonar sends sound waves from a ship to the seafloor and measures the time it takes for echoes to return, allowing researchers to calculate depth. As sonar technology improved, multi-beam echo sounders were developed, providing not just a single depth point but a wide swath of the seafloor with high resolution. In parallel, satellite altimetry offered a complementary perspective, detecting subtle changes in sea surface height caused by gravitational variations due to underwater mountains, ridges, and trenches. While satellites cannot achieve the same resolution as direct sonar, they provide a global overview that guides targeted mapping missions. Modern mapping projects are colossal undertakings requiring international collaboration, data sharing, and sophisticated processing. One of the most ambitious initiatives is the Seabed 2030 project, launched by the Nippon Foundation and the General Bathymetric Chart of the Oceans, aiming to map the entire seafloor by the year 2030. This project gathers data from ships, satellites, autonomous underwater vehicles, and submarines, combining decades of historical measurements with new surveys. The result is a dynamic and continually improving map of the oceans that informs everything from navigation to climate science. The topography of the seafloor is far from flat. It is a landscape as diverse and dramatic as any on land. Undersea mountains, known as seamounts, rise thousands of meters from the abyssal plains, forming habitats for unique marine life. Some are extinct volcanoes, while others are active, hydrothermal vents spew mineral-rich fluids that sustain ecosystems independent of sunlight. These undersea features play a crucial role in ocean currents, nutrient distribution, and even global climate regulation. Trenches, the deepest parts of the oceans, such as the Mariana Trench, plunge nearly 11 kilometers below the surface. These trenches are formed by tectonic activity, where one tectonic plate dives beneath another, a process called subduction. Mapping these extreme environments allows scientists to study seismic activity, earthquake risk, and the formation of the Earth's crust. Abyssal plains, often appearing featureless, cover vast regions and act as sediment sinks, accumulating materials that provide historical records of ocean chemistry, climate, and life over millions of years. By mapping these areas, researchers can better understand past climate shifts and predict future changes. Mapping also aids in the protection and management of marine biodiversity. The identification of undersea mountains and seamount chains allows for the designation of marine protected areas, crucial for conserving species that are sensitive to human activity such as deep-sea mining, fishing, and pollution. Moreover, high-resolution maps are essential for safe navigation and the laying of undersea cables that connect continents. The modern mapping workflow integrates multiple technologies. Ships equipped with multi-beam sonar systematically survey the seafloor. Autonomous underwater vehicles descend into deep trenches carrying sonar, cameras, and sampling equipment. Satellites measure sea surface height anomalies to infer large-scale structures. Computational models process and combine these datasets into continuous, detailed digital elevation models of the seafloor. These models can be visualized in 3 dimensions, revealing the folds, ridges, and canyons of the underwater world in astonishing detail. One remarkable finding from global mapping is the intricate network of mid-ocean ridges, stretching over 60,000 kilometers. Where tectonic plates diverge and new crust is formed through volcanic activity, this global ridge system is fundamental to plate tectonics, driving seafloor spreading, shaping continents, and influencing ocean currents. Mapping also revealed the presence of previously unknown features, such as undersea landslides, submarine volcanoes, and massive deep-sea coral reefs. Each discovery not only expands scientific knowledge, but also underscores the complexity and dynamism of the ocean environment. Another vital application of seafloor mapping is in understanding natural hazards. High-resolution maps allow researchers to model tsunamis, predict areas at risk from underwater landslides, and anticipate volcanic eruptions on the seafloor. These insights are crucial for early warning systems and disaster preparedness. The project also emphasizes the collaborative nature of modern oceanography. Data is collected by research vessels from multiple countries, processed through shared databases, and made available to scientists, policymakers, and educators. Open access mapping ensures that the knowledge benefits humanity broadly, fosters further research, and supports sustainable management of ocean resources. Mapping the seafloor is not without challenges. The oceans are vast, deep, and hostile environments. Ship-based surveys are expensive and time-consuming, deep trenches are difficult to reach, and adverse weather can halt operations. Autonomous underwater vehicles are limited by battery life and communication constraints, and satellite measurements, while global, cannot yet match the resolution of sonar surveys. Yet despite these challenges, the progress has been remarkable. Decades of dedicated effort have transformed the oceans from unknown expanses to landscapes that can be studied, navigated, and managed with increasing precision. Mapping the seafloor also provides a historical record. Sediment cores and bathymetric data reveal past tectonic events, volcanic eruptions, glaciation cycles, and sea level changes, helping scientists reconstruct Earth's geological and climatic history. The benefits extend to education and public engagement. Digital visualizations of the seafloor inspire curiosity, illustrate complex processes, and bring awareness to the hidden majority of our planet that lies beneath the waves. As global interest in the oceans grows, seafloor mapping becomes central not only to science, but also to policy, conservation, and exploration. Humanity is uncovering a world that is as alien and dramatic as any mountain range or canyon on land. From hydrothermal vents that host life independent of sunlight to trenches deeper than Mount Everest is tall, the ocean floor is a frontier of discovery, reminding us of the power, mystery, and fragility of our planet. In the coming years, as Seabed 2030 and other initiatives advance, we will have a comprehensive, high-resolution picture of the Earth's hidden topography, enabling better stewardship of the oceans, improved understanding of climate systems, and new insights into geology, biology, and oceanography. This endeavor reflects human curiosity at its best, the drive to see, understand, and preserve, combining centuries of observation, cutting-edge technology, and international collaboration to reveal the face of the planet that has long remained hidden beneath the waves. Mapping the seafloor is not merely a technical exercise, it is a story of exploration, discovery, and responsibility, showing that even the most remote and seemingly inaccessible parts of the Earth are connected to our climate, ecosystems, and survival. The data produced by these efforts will guide sustainable fishing practices, predict natural disasters, support undersea infrastructure, and expand our knowledge of life in extreme environments. As technology improves, we can imagine fleets of autonomous submarines continuously surveying the deep, satellites refining measurements, and AI analyzing enormous datasets to detect patterns, anomalies, and changes over time. The global seafloor map will not only be a scientific resource, but also a cultural and educational tool, inspiring generations to value the hidden world beneath the ocean, and to understand that what lies beneath the surface affects everything above, from weather patterns to biodiversity, from tectonic stability to the livelihoods of millions who depend on the sea. The story of mapping the seafloor exemplifies the convergence of human ingenuity, collaboration, and perseverance, reminding us that exploration is ongoing, knowledge is cumulative, and even the most challenging frontiers can be illuminated by curiosity and determination. And that was our journey into the hidden world beneath the waves, exploring the global seafloor, The mountains, trenches, plains, and volcanic ridges that shape our oceans, influence climate, support diverse ecosystems, and hold secrets of Earth's past. If you enjoyed this deep dive into oceanography, discovery, and the science of mapping the unseen, please like this video. Leave a comment telling us what fascinated you most about the ocean floor. And subscribe to Little English Studio for more stories told in clear and beautiful English. Until next time, keep exploring, stay curious, and remember that some of the most dramatic landscapes on our planet are hidden from view, waiting for human curiosity and determination to reveal them.